Hi, welcome back to my project box. In this video I would like to take a look at this old juicer to make things like carrot juice. It's a Phillips juicer and it's given up the ghost. It stopped working. It doesn't belong to me. It was given to me by my sister-in-law, which claims this one is better than any other juices she's ever had. So she has another juice machine, but she likes this one a lot, and she's quite sad that it broke. And at once she's had it for years, and she'd asked me to have a look to see if I could fix it, because she doesn't really like her new juice machine as much as she likes this one. So she claimed that she plugged it in and used it, and it made a very loud humming noise, and then tripped the circuit breaker on the fuse board, and then just stopped working after that when she reset the circuit breaker. So hopefully it's not completely burnt out. If anything, it's going to be a bit of fun to see what's inside here, and you know, see how it works, if it's got any fancy electronics in it, and maybe we can fix it, and I'll do some explanations of what I think is going on. So let's have a look. It's quite big, so it doesn't really film very well on my bench, but we'll give it a go. So let's take it apart. It's seen better days. It's got cracks and things on it, but for some reason she really likes it, so if I can fix it I will. It's a bit grubby. So it's got this sort of grating thing, and the centrifugal force spins the juice through this sort of net filter sieve thing. It goes out the spout here. So let's take this thing apart and we'll see what's what. Now in the UK we have fuses in the plugs, so it could be that the fuse in the plug is blown, so we can take a look at that. So it's got a 13 amp fuse, and as you can see we've got continuity. So the fuse didn't blow, which is quite surprising, but the circuit breaker can trip quite quickly before the fuse gets time to blow on a dead short. I've seen that before. Okay, so the plug fuse is okay. So let's take it apart and see what's inside. It's nice and simple, just 4 screws. There we go, we're in. So we've got, by the looks of it, we've got a little PCB, and we got a, it looks to be like a permanent magnet motor. See, there's a big magnet there and a big magnet on the other side, so they're like field magnets. So which means that this motor has to run on DC. Normally in these type of things, or very often in these type of things, they use a universal motor or a series motor, series 1 motor. And these universal motors, they have basically coils on the sides where the magnets are, which means they can run on both DC or AC. And of course this is running off of mains electricity, so if they use a universal motor they can just run it straight on AC. So you'd need some sort of rectification, and if we look inside we can see there's 4 diodes there, so I assume that's a bridge rectifier, so we can get our DC to run this motor on DC. It's strange that they chose to do that. Don't know why. Maybe they get more torque from these magnets here. Don't know. Yeah, normally they're the universal motors. I'll explain that a little bit later in the video, the difference between a permanent magnet motor and a universal motor. But this one needs DC to work, hence I guess the red wire here for positive and the black wire for negative. Well, let's try and power it up and see if it runs. So I think we have little safety switches down there, little micro switches, one on either side. And I guess the incoming supply passes in series through those safety switches. And it won't run unless the machine is fully put together. So I guess we need to try and do that. So let's plug it in and see if it works. No, she's completely dead. Let's I've taken the thing off, so let's turn it around. Now let's pull this little electronic control board out and see if there's anything wrong there. It's possible the motor could still be okay. Let's pull the little control board out and see. Just putting a little bit of blue tack on the end of my screwdriver so that we don't lose our screws. Let's have a look. Let's check if the fuse has continuity. Well, we certainly got a blown fuse there. And if that fuse is blown, it's likely something else is wrong on this board as well. Because there's a lot of current to take out a fuse. It looks like one of those slow blow fuses as well. It's also got these MOVs, which are like metal oxide resistors, and they're for suppressing transient, so they're transient suppressors. I've got a bit of a love-hate relationship with these because they can fail short, and they can also overheat and burst into flames. So I really don't like them. I normally don't put them in my projects because they cause me more grief. They do more harm than good. In my particular case, let me know in the comments what you think, if they're worth putting into your circuits. Personally, I don't like them, and I generally remove them whenever I see them. Because if these MOVs triggered, they can actually blow your fuse. So I'm going to simply remove them now from the circuit so that it's one less thing to troubleshoot, and it'll work just fine if it didn't have them in circuit. So they're coming off. And this is an old machine anyway that I just want to sort of revive, if possible, breathe new life into it. Right. So we've blown our fuse. So I think the next thing to check is, did we blow any of these diodes? Let's have a look to see if there's any tracks blown underneath on the circuit board. Oh, yeah, it looks like there is, yeah. Looks like this track is blown clean off, and that track is completely blown off. So basically a lot of current, like dead short or something. Or maybe one of the diodes blew and then created a dead short. Could be maybe the motor was overloaded and that caused the diode to blow, and then it felt short circuit, and then the tracks blew off, took out the fuse. Well, let's check the diodes. I'm going to just take one of the brushes out from the motor so we don't get a continuity through the motor. So yeah, now one of the brushes is not making contact, so that shouldn't give us strange readings now. So let's try again. That's definitely a blown diode. And this diode is okay, it's got about a 0.5 volt drop. That's short circuit, that's short circuit. So I guess we need to replace the diodes to make a new bridge rectifier. Now we can either put in a complete full bridge rectifier.
To make a full bridge rectifier. That's right, it's not a dumb single diode rectifier, it's a full bridge.
Or we can put a ready-made one in. But I've got some diodes, they're not exactly the right type. They're a bit bigger. I've got some of these diodes here. They're in a bigger package, so they can handle a bit more current. These were salvaged from something else. So I think if we can sort of put them in, or sort of hack them in, or brute force them in somehow, then that should be okay. Even though they're old diodes, they're bigger ones, so it should be good. As long as the voltage rating is correct. Now, what else is on the circuit board? Well, we got some suppression, we got some filtering, basically for interference suppression, stop any noise from the motor making its way back to the rest of the appliances plugged into your home. And we also have what looks to be a triac. And maybe a diac, or a diode or something there. So I guess this is like a trigger circuit for this triac. And this is probably for speed control. So we probably have full speed and low speed. And looking how this is connected, you have this switch here, that 2-position switch. You have off in the middle and high and low. Yeah, it looks like this is the high position and this is the low position. So it looks like the high completely bypasses this circuit here, and the low is basically the speed is reduced with this little bit of circuitry here, which is a bit silly really, because you can do it with just one diode. So you get half wave going to the motor, half wave DC instead of the full wave rectified, full bridge rectified. You just do a one single diode and you switch it with a switch, and you get half wave going to the motor, and half the power, half the speed is effectively. Half of the sine wave only makes it through, so the motor runs at a lower speed. I don't know why they went for this fancy triac speed control type thing. It's almost like a dimmer circuit, but I would have just used a diode for half wave. Anyway, so I think we should replace these diodes and see if that brings it back to life. So I've got the diode soldered out. I had to do it off camera because it was a bit tricky to do and difficult to film. So I've got these fatter, bigger diodes. They're high enough voltage rating. I think they're rated at 400 volts, which is fine. And the current, I think, is 4 amp diodes. So they're a bit beefier than the originals, but I had to put on these bodge wires, and I think I'm going to need that to make them fit in. Nothing wrong with a bit of bodging, as long as it works. So we'll put these in, solder them in, and I think we need to fix those broken tracks as well. So let's get the polarities the right way around. Luckily it's indicated on the PCB. Let's solder those in. Right, I've got them all soldered in, but the pad there is broken because the track's blown off, so we'll have to repair the track as well. But we'll cut all these off, all these extra lengths of the leads off, and then we'll repair the track as well. So not pretty, but functional, and I think at the end of the day, if nothing shorts out and it works, that's all what we need really. So let's fix that broken track. We need a bodge wire soldered from there all the way around to there to fix that broken track. There we go. Our broken track has now been repaired with some bodge wires, and that pad there that was broken, the diode lead, is just coming out and joining the bodge wire and fixing the track along there. So I guess it's time to test to see if it springs to life or if something else blows up. I don't know what caused this diode to blow. maybe motor overload. Oh, of course, one more thing. The fuse is blown. This fuse here is blown. Now, normally I would say you absolutely have to change that fuse. But in our case, because we're in the UK, the plug is already fitted with the fuse. So if anything goes wrong here, in theory the plug fuse, if you put the correctly rated fuse, should blow. So it's really belts and braces having two separate fuses, one in the plug and one here. I guess if this was to be used in Europe and the rest of the world, you would need this fuse, absolutely would need this fuse to prevent any sort of fire from happening, or because then you're just relying on the circuit breaker tripping rather than this fuse. And then obviously the flex needs to be able to handle the current of tripping the circuit breaker. So what we'll do is we'll just simply link this fuse out. We can either remove it or just solder a wire on top. Normally I would never recommend you do this, but that wire is not going to be a fuse. We're going to rely on the fuse and the plug. So I've soldered a little thin little wire across the fuse. It's not thin enough to be a fuse wire, so we're not actually relying on this wire being a fuse, because we're relying on the plug fuse. So effectively the fuse isn't there. But some people would actually do that, would solder a thin wire across the fuse. The trouble with that is you don't reliably know what rating that wire would be, the fuse wire would be. It's better than nothing, I guess. You can make a little PCB fuse with a thin little wire. I've seen people do it before. Wouldn't recommend it though. This is just a linked out fuse. It might as well not be there. So maybe we should test the motor first with a something like a 12-volt battery, because it's a DC motor. We can probably run it on a lower voltage like 12 volt, and it should spin if there's nothing wrong with the motor. So let's give that a try. So I have like a 12-volt battery, one of those little sealed lead acid batteries. So if we get the polarity right, so this is the red wire. So if we put positive on that, on the motor, on one of the brushes, and this is the black wire, which I assume is negative, and we'll stick that on one of the brushes as well. And if everything is good, the motor should spin. So let's try. And if you look at that, the motor is actually turning on 12 volts. Obviously it's not its full voltage, but it is turning at a slow speed. This leads me to believe that the motor is okay. So I think we can safely power it up on mains voltage now, and hopefully nothing will trip out and nothing will go bang. Now what I'm going to do is I'm going to power it through this lamp as a form of current limiting. That way, if anything goes wrong, like if there's a fault or a dead short circuit, it won't trip the circuit breaker or blow a fuse. The lamp would light. It's a 1000-watt lamp, so it can pass quite a lot of current. You can use something like a hair dryer or something like that, or a little heater to do the same job. It just allows you to do testing without catastrophically blowing something up or blowing a fuse if there's a fault. So this is our current limiter. So we need to bypass these little safety switches at the bottom. So I think in order to, the simplest way to do that would be to assemble the top piece that pushes those little safety switches in. Let's zoom out a bit. So we got our safety current limit. So let's give it some power and see what happens. Right, let's try the low speed setting. That's low speed and full speed. So that looks like a successful repair. So if I was to design this circuit, I would probably do it a bit simpler, because we need our full bridge rectifier to give us DC to the motor, and the motor is simply just tacked directly on the output of the bridge rectifier. So here we have the simplified version of the circuit without any of the interference suppression, and it's basically a brushed DC motor, permanent magnet one, connected directly to a full bridge rectifier, and it can either connect to the low speed setting, which is basically a triac sort of light dimmer style circuit, which generates the low speed by chopping the AC waveform at certain points, so basically turning it on at certain time intervals on the AC waveform. The time delay is generated by this resistor and capacitor. So the capacitor charges via the resistor until a voltage threshold is reached, and then the dioc will fire and it will trigger the gate of the main triac, and that will turn on a certain point of the AC waveform. And by doing this repeatedly, you get a speed control. Now normally on this type of circuit, you would have a variable resistor that can be adjusted for different speeds or different power levels. But in this circuit, they've chose a fixed level. And for the high speed setting, the selector switch just bypasses the triac circuit and puts the main voltage directly on the bridge rectifier, and then the motor spins at full speed. Now I personally think this circuit is a bit overcomplicated, and you can replace this whole triac circuit with just a diode, and that would give you half wave DC, and it would effectively give you half the power and half the speed, and it's much simpler. And the selector switch would only need to bypass the diode to get full speed. That way the full bridge rectifier rectifies the AC waveform completely, and you get full speed. So let's test my theory. I am powering it via a diode just before the bridge rectifier, and then this switch will simply link out the diode. So when the diode is linked out, it gets direct mains voltage, 230 volts, and if the switch is turned off, it gets half wave, so effectively half of that. So let's power it on and see what it does. See, that's full speed. You can hear the speed change. Now I suspect one of the reasons they didn't do that is because they can set the exact desired speed they want with the triac circuit. I don't even know why they have a high and a low speed on this thing, because when you use it, you always use it on maximum. Anyway, so that works as a simple repair. There we go. Let's put it back together. Let's make some juice. There's actually a big skid mark in there for when it blew that track away. Now, of course, I'm going to use my little blue tack on the screwdriver trick. If we can use a magnetized screwdriver as well, but this is guaranteed not to drop, because you don't want that little screw to fall inside the machine, because that could be disastrous. Make sure there's no wires snagging anywhere. Let's put the cover back on. Right. One hopefully fully working Phillips juicer. Right, let's put this, let's assemble this thing. I think this bit goes here. This is your strainer and sort of grinder that grinds the fruit or carrots or whatever you want to juice up to a pulp, and then the centrifugal force will then force the juice through this fine mesh, and then it will come running out there. I think your pulp goes in this bucket at the back, I'm not sure. Right, I have here in front of me a plate of the finest British carrots, or at least I think they're British carrots, and some apples. let's make some carrot and apple juice. We'll put my cup here to catch the juice. Let's give it a go. Cheers, bottoms up. Amazing. Carrot and apple juice. Not really my cup of tea, but it seems to work just fine. Now I'm going to give this to the missus to clean. No, just joking. I'll have to clean it myself. But I can now give it back to my sister-in-law, and I'm sure she'll be happy to have her old favorite juicer back. Some extra life breathed back into it. Now she can take her new juicer that she doesn't like and put that in the bin and go back to the old one that she likes. Anyway, thanks for watching. Let me know in the comments what you think of this repair. Is it too bodged? Is it too sort of quick and dirty repair? Or is it acceptable for a really old machine like this? And let me know what you think about motors and how they work. Anyway, catch you guys on the next one. Thanks for watching.